So the other day we talked about Mendeleev and about the production of the periodic table, and we talked about the effective nuclear charge, which was in this slide here. We talked about the differences between valence versus a core electron and how you figure out the effective nuclear charge. Remember, effective nuclear charge is equal to the core, or the valence, the total minus the core electrons. And really what it comes down to is this. So for example would be fluorine has 9 valence electrons. If you go through and figure this out, so looking at the periodic table, fluorine has, actually, you know what, I don't know why I said 9. Fluorine has 8, why do I keep doing that? 7 valence electrons. Fluorine has a total of 9 electrons. So now, so if it's got 7 valence electrons, when we look at the simple mathematics, so 9 minus 7 gives me 2 core electrons. And so if I want to figure out the effective nuclear charge, I take 9, which is the total, minus 2, which gives me plus 7. So the effective nuclear charge on fluorine is plus 7. There are 7 valence electrons. So remember, the valence electrons are on the outside. Normally, what will happen is that the effective nuclear charge and the valence electrons should match up. So if you have an atom that has 6 valence electrons, the effective nuclear charge will be plus 6. They should cancel out as far as charge is concerned to be equal 0. So that's sort of a shortcut to figuring that out if you understand that, but it's real quick and easy to at least calculate it if you wanted to. So doing another one, let's not do bromine. Let's do selenium, just so we have one that's a little bit bigger here. So selenium, all right, so selenium has 34 total electrons. So 34 total electrons. All right. And so to figure out the core electrons, what I'm going to do is look at the fact. So it's got 6 valence, so minus 6, so that's going to be 28. And 34 minus 28 gives me plus 6 for the effective nuclear charge on selenium. So selenium's charge would be plus 6, whereas fluorine would be plus 7. And also the fact is that if you look at the valence electrons, there are 6 valence electrons for selenium, so the plus 6 and the minus 6 cancel out. Keep in mind that valence electrons are negatively charged, so it'd be a minus 6. All right, so that's how we deal with the effective nuclear charge. And so the PowerPoint has its own equation. In fact, this is the real equation here. I Sheltonized the equation. Oh, come on. I Sheltonized the equation here. So this equation is just a little bit easier to understand. But when they talk about a screening constant, the screening constant is really referring to the core electrons. The core electrons screen, help to shield the nuclear charge from the valence electrons. That's what that is really all about. So don't try to be, don't get just concerned about this equation and what Z and S. Z represents the charge, the total number of electrons, and then S just represents the screening constant, which is basically the core electrons. That's all it is. All right, so now we talk about the different trends on the periodic table. So there's atomic radius, there's ionization energy, there's electron affinity, there's electronegativity. So there's 4 different trends that you're going to look at on the periodic table We're only going to look at 3 of those in this chapter here, and then we get into the next chapter, we will talk about electronegativity specifically. So the first trend deals with the size of an atom. We also call this atomic radius. So when we talk about the atom, so this example here is actually of hydrogen gas. All right, and so hydrogen, the atoms themselves overlap each other slightly here, but so what we do is we measure the distance from here to here, and half the distance represents r, your radius. So when we talk about the atomic radius, we're really referring to the radius from the core of the electron, the core of the atom, to the outside of the atom here. So the radius is dependent on, you know, the atom, how many electrons it has, and its location on the periodic table. So we're going to study that pattern over the next slide or two. So so here's the basic layout of how the size changes in relation to the periodic table. So you can see, I'm just looking at the picture here. I'm not even worried about the writing that's on the right hand side. If you're concerned with that, there's the next point. But I'm more concerned about the fact that rubidium is the largest element on this periodic table right now is what we're looking at. In fact, they're missing another row here. And then helium is the smallest. So as you go to the left and down on the periodic table, your size is increasing in this direction. So the patterns you see on the periodic tables, if I just draw a basic periodic table, is you have an arrow drawing down towards the bottom left-hand side, which that represents the atomic radius. Okay, I'm just going to write this, abbreviate this AR, and it increases in that direction. So it increasing right to left and top to bottom. All right. So now we come to the question as to why does it change in size in this specific manner, in this pattern. So we can talk about this best. It's very easy to talk about this when we look at going top to bottom. We'll talk about that first. So I'm going to pull up one note here because I definitely want to jot a couple other notes in here. Like it's hard for me to do that on the PowerPoint. So we have the nucleus here. So we go to the first period on the periodic table, starting with hydrogen, and you have your first shell. All right, so keep in mind that as you go down the periodic table, what's going to happen to your value of n is going to increase. And so as we go to n equals 2, it's going to be a little larger, n equals 3, n equals 4, n equals 5, n equals 6, and then we have 7. Obviously, as you can see, as you go from top to bottom, it gets a little bit bigger as you go from top down. So it increases in that direction. That's why the size, the pattern is in that direction of change. It increases from top to bottom because the more electrons you add in, the more orbitals, the more stuff you got to pack in there. So it's going to get bigger automatically. It's just like your book bag. You start off with just one class. You've got one book in there. Then you add on to a second class. You get a second book put in there, and your book bag grows as you add more and more classes to it. And so same thing here. The more electrons you add in, the bigger it's going to get. Now that's talking from top down. So the other pattern that you see on the periodic table is that as you go from right to left or left to right, depending on however direction you want to go, we're just going to talk about going from left to right. Okay, so we know the pattern is increasing from right to left, but the question is, why is it that it decreases from left to right? So if we were to focus on the specific elements that fit into this pattern here, okay? So why is it that it decreases? So why does it decrease? And it is the atomic radius going from left to right. All right, so that's the question here. All right. Does anybody want to kind of think about this out loud? Why would you think that? What would you say to try to explain why it decreases from left to right? What do y'all think would be the cause of it? So we have big over here and small over here. What does anybody have any idea as to why that might take place and what the reasoning behind it is? You don't have to be right. I'm just curious if you guys have any thought towards it.
The only thing that I can think of is maybe there's more room in between the orbitals.
Okay, maybe, maybe not. That's a good thought, at least.
Like there's a lot of empty space on hydrogen or something. I don't really know.
Well, I mean, that's what I would expect y'all to think because you only have so much information given to you. Now, I will say this: we talked about Aufbau's principle the other day with electron configurations. It said that as a proton's added in, you add an electron. What's the charge of a proton?
Positive.
Okay, so as we go from left to right, so that we add one proton, this is +1. We go to the second, we add another one, that's +2. And so this is going to grow in positive charge all the way across the periodic table. So the very final row or group here has +8. So he also states that as the proton's added, the electron's added in. Okay, so if your charge of your nucleus becomes larger and more positive, what's going to do? How is that going to affect the electron itself? Is that going to make the electron be more repelled or more attractive to the nucleus?
Attractive.
Right,
Attractive.
exactly. So attracted means to pull close to you, does it not?
Yes.
All right, that's why. All right, so as you add more protons, the electrons in the outer shell are more attracted to the core of the nucleus of the atom. All right. As a result, the size of the atom decreases as you move from left to right on the periodic table. So it's all about the attraction of the electrons and the protons on the periodic table. All right, so that's the answer to this question here. So the explanation of the way the periodic trend happens on the periodic table in relation to the size, it all depends on the top to bottom where you adding orbitals in versus adding protons left to right. But the long story short is, for the periodic table trend, as you go left to right, top to bottom, the size will increase in that direction. Now, if we start to talk about the ions specifically. So right now, this just refers to simple atoms that have no charge or anything, right? So now, what happens to the size of an ion compared to a neutral atom? So that's the question we're going to answer now. And so we go about this by just looking at a very simple element, sodium, all right, versus sodium with a +1 charge. Now, I want you to understand that with sodium, sodium has a it's got a +1. All right, I'm gonna need a different color here. Come on. So it's got a +1 nucleus, and then, oh my gosh, it drives me crazy. All right, and then on the electron cloud, that is the absolute worst circle I've ever seen. It's got a -1 electron. Okay, so right now it's neutral. So the sodium atom is neutral. Now over here, and the +1 atom, it still has a +1 nucleus, but there are no electrons in the outer shell. So it's 0 out there. So that means that we've lost an electron. Now for sodium, sodium is not lacking electrons because there are actually 2 inner shells. Okay, so with the sodium, all right, that has the 1 valence electron, you have this 1 valence electron in the outer shell. Now for the sodium with a +1, you take away that outer shell because you've lost that 1 electron because it's a +1 ion. So when you look at these 2 drawings here, what happens to the size of sodium when it loses 1 electron? Does it increase, decrease, or stay the same? What do y'all see from the drawing there?
It decreases.
Exactly. So when we compare the neutral atom to the +1 atom, it decreases in size as you go from neutral to +1. So this is neutral, and this one's +1. All right. Now, the long story short here is that cations, remember that's a fancy word for just saying positive, cations decrease in their size, atomic radius specifically here, in their atomic radius. Now, the other one is referencing the anions. All right, so anions are negative charge. So let's look at that, and that we'll fill that in just a second here, right? So let y'all have a second to write that down. So we have a difference between oxygen versus the oxygen with a -2 charge, which is reference to oxide. So the neutral atom for oxygen has, what is it? So it's got 2 different energy levels because on the second, n equals 2. And it's got 6 valence electrons. So 1, 2, 3, 4, 5, 6. Now, one thing we haven't talked about is the fact that we're going to be dealing with what is called the octet, which means 8. So the most electrons that you're going to have in the outer shell is going to be 8 valence electrons, okay? And so when we look at the drawing for the oxygen with the -2, you still have the 2 levels here, okay? The 2 energy levels. So we have 6 here. Now the difference here is we have 2 more electrons added into the electron cloud. Now my question for you is that remember the electron's negatively charged. The neutral atom is perfectly fine. It's neutral, everything's stable. But now I'm going to add in 2 more electrons into the electron cloud. How do you think that's going to affect the stability of that electron cloud? Do you think that it's going to make it more stable, or do you think it's going to make it more unstable? What do you guys think? Think it's making it more stable or more unstable?
More stable because now it has 8.
Okay, well, which
like
one's neutral? Oh, I'm gonna stick with you. It's Sydney, right? That's who was talking. Is that right, Sydney?
Yeah, yeah.
Okay, so which is neutral? The one that's on the left or the one that's on the right?
The one that's on the left.
Okay, so neutral means the charge is what?
0.
All right.
Not positive or negative.
Okay, so now if you add 2 more electrons in, it's no longer neutral, is it?
No.
What's the charge in this case when I add 2 extra electrons?
-2.
Now, so let's say you take 2 magnets, so you've got 1 extra electron, you have 2 extra electrons, put them together. If you try to put the south, and you ever play with magnets before? Just curious.
A little bit.
All right, if you take the south pole and the south pole and you stick them together because they're both negative, are you ever going to be able to cause them to stick together?
Probably not. They repel each other.
So if you put 2 extra electrons in, they're going to repel each other, is what you're telling me, right? If they repel each other, is that going to cause this -2 to be more stable or more unstable?
More unstable.
Yeah, exactly. So if it makes it more unstable, what happens is that this is actually what you're going to see. So the repulsion causes the electron cloud to actually expand and grow. So when you compare that to the neutral atom, oh my. When you compare that to the neutral, you see that the negative charge does what? It causes the electron cloud to not decrease, but to increase. So as we go from here, the electron cloud increases, so the atomic radius itself increases naturally. So anions cause the atom's atomic radius to increase due to the extra repulsions experienced. And I'm actually going to add a little bit into there. Experienced in the electron cloud. So as you guys finish this, I want you just to listen. The more positive it is, the smaller it gets. The more negative it gets, the larger it gets. I'll repeat that. The more positive the atom becomes, the smaller. The more negative, the larger. Everyone understand that? So as we are talking about this, I want to just bring up a term here. Isoelectronic. This all goes back to the configurations, the electron configurations specifically. So I'm going to draw out sodium and sodium +1. So we have a couple examples to go off of here, okay? So sodium is 1s2, 2s2, 2p6, 3s1. That's its configuration. Sodium +1 is 1s2, 2s2, 2p6, because you lose this 3s1 electron because it's +1. All right? Does everyone understand that? So this one decreases in size because you lose that extra orbital. Now, when I look at oxygen, oxygen's got 1s2, 2s2, 2p4. That's its configuration. We just talked about oxygen with the -2 having a larger radius. All right, now oxygen with a -2 is 1s2, 2s2, 2p6. So as you add the extra electrons in, you cause the radius to increase. So it increases in size because you add those extra electrons in. Now, which of these 4 configurations are isoelectronic? Now, iso means what? What does iso itself mean as a prefix?
Two?
Mm,
No.
not 2. Good try, though. Iso means to be the same. So which one has the same electron configuration? Of these 4 that you're looking at, which one has the same configuration?
Sodium +1 and O2-.
Yeah. So I'm going to underline those. So if you look at this, when we talk about isoelectronic, we're looking for configurations that are the same. So we would say that the sodium with a +1 and the oxygen with a 2- are isoelectronic. And that's because they have the same configuration. Now, does that mean that they are the same element? No, they're not. They're still sodium with a +1 and oxygen with a -2. It's just that they happen to have the same electron configuration, which results in being a noble gas. In this case, it would be neon as your noble gas. So these two, remember, when we, not really remember, but remember this for the future, okay? Noble gases are what the elements want to be like. And so what they'll do is they'll lose electrons or they will gain electrons, so that way their electron configuration will match that of a noble gas. In our case, the noble gas that these 2 elements are trying to match is neon. So the goal is to be neon. You want it to be like a nobleman. Noblemen are people with high prized possessions. They're of notable status. Does that make sense? And so these elements are trying to be like the noble gases. Does everyone understand that? Remember, isoelectronic has the same electron configuration, so what you have to do is you have to write the configuration based off of the atom or ion, and then you just match them together to see if anything is the same. If it's the same, then like the sodium +1 and the oxygen with the -2, we can say that they are isoelectronic. Are there any questions with that? Okay. All right, so now what does that do? It leads us into the next part. All right. In fact, y'all, let's do 3 problems today. I haven't done this. So let's do a couple practice things here, okay? So I'm gonna put up 3 problems, okay? So 1, 2, and 3. What I want you to do is figure out which is the larger atom or ion from each pair. So sulfur or S with a 2-, calcium or calcium with a 2+, and the last one is Br- or krypton. Okay, so I'm gonna give you 2 minutes. I want you to look at this and figure out which of the 2 in each pair are larger. Okay, so you don't have to try to explain it, just answer the question. So which of the 2 are larger? I'm gonna give you 2 minutes. That's 10:36 on my watch, so go ahead and get started. You do need to have an answer when I come back. So 2 minutes. Go ahead. Okay, so that's 2 minutes. Fast. All right, so we look at the number 1 here. So which of those 2 is going to be larger? Anybody want to volunteer?
Sulfur.
Go ahead. I know y'all 2 people said something at the same time. What'd y'all say? Y'all got cut off.
You can go first.
Okay, sorry. The sulfur will be larger.
Well, there's 2 sulfurs here, so which one are you talking about?
The first sulfur will be larger.
Are you sure about that?
Yes.
Are you certain? What's the charge on the second one? Is it +2 or -2?
The second one is -2.
Okay. What did I tell you earlier that happens to the atom when you add extra electrons into it?
It becomes more unstable
So
and gets larger, right?
read this. Read this here for me right now. Just do the best you can. Read that.
Anions cause the atom's atomic radius to increase.
Due
To the
repulsions
repulsions
experienced in the.
experienced in the electron cloud.
So which one has extra electrons here?
The 2 minus.
So you want to change your answer?
Yeah.
Okay. All right. Everyone, thank you very much, by the way. It's a growing pain, isn't it?
Yeah.
Better to have that growing pain now than on the test, wouldn't you say?
Yeah, definitely.
All right. No, you're good, man. Thank you very much. All right. Someone different. Number 2. What do you guys think? Don't be scared because you feel like you're going to be wrong. It's okay. Sometimes it's actually better to be wrong because it's a learning experience for everybody. So what do you think? Calcium bigger or calcium plus 2? Which one do y'all think? Anybody?
Calcium?
Right. Yeah. So it's calcium. And that goes to the fact that plus 2 represents cations, and cations are smaller because you lose that repulsion. Right? So great job. Good. All right. Now we have a difference between bromide, which is Br minus 1, or krypton. So which one is bigger?
Wouldn't they be the same?
Why do you say that?
Because bromine has 35, and because of the -1, it would become 36, and krypton already has 36.
Now that's exactly what I expect you to say. Very good observation. But I want to point out one thing here, okay? So the electrons on the bromide is 36. The electrons on the krypton is 36. Now we look at the protons for each of these. So the number for bromine is 35. And the number for krypton is 36. So which one of these are neutral? So this one is neutral, where this one is not. There's a difference here. There's one extra electron in bromide as compared to krypton. So now I understand why you said that they are the same, but the actual reality is that bromide is larger than krypton because the fact is it has one extra electron, and that causes repulsion in the electron cloud. Does that make sense?
Yeah, that makes sense.
Perfect. All right. Does anybody have any questions about either of these 3 that we just looked at? All right, very good. So now that leads me to the next section in your textbook, which deals with ionization energy. So I'm going to come back to the PowerPoint. All right, so I'm going to go ahead and get back here, and we're going to go ahead and move on. I'm going to stick with the PowerPoint for today. We have about 10 minutes left in the class here, and then we'll be done. So we're going to get as far as we can get right now, and then I'll finish this probably on Wednesday. So for now, let's just take some basic notes. So go ahead and write down this bullet point here, please. And I'm going to go ahead and pull up the second one here. So go ahead and pull those up, write those down. I'll be back in just a minute. Okay, so the ionization energy is the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. Ground state, again, is just referring to how stable the atom or ion is. And so we're going to use human beings as an example here. All right. Now I'm going to pick on, let's see here, Devin. Who else am I going to pick on? I'm going to pick on, I'm going to pick the same people too much. All right. Let's pick on Cassandra and Devin. All right. So Cassandra, can you turn your mic on or where you can talk to me?
Yeah.
All right. Do you carry a pocketbook?
No, I don't.
You don't? Well, I can't use you then. Josephine, who does anybody carry a pocketbook here?
I do.
All right. So I guess anybody else carry a pocketbook, or y'all don't? Y'all must not carry pocketbooks anymore. Sydney's the only one that carries a pocketbook. Okay. How many we got? I don't think people want to talk to me. That's what it is. Temperance, do you carry a pocketbook?
No, I don't.
You don't carry? Well, how? You don't
I
carry
just,
any? Well, how
I
you
just
carry your
carry a
stuff
wallet.
around? You carry a wallet.
Yeah, like one with the strap, so you can just carry it on your arm.
Is that not considered a pocketbook? Or like a pocketbook? No, I guess not.
No.
Yeah, you can't fit with so much in that, can you?
Yeah, it's just a wallet with a strap.
Devin, do you carry a pocketbook?
No, I just have a wallet to put in my pocket.
Okay, today you're going to carry a pocketbook. So
All right.
Sydney's the only one that carries a pocketbook in this room, and now Devin's going to be, okay? So let's say that you both are walking down the streets in New York City, right? Now, obviously, Devin really doesn't like his pocketbook, so he holds it out away from his body. He's like, I don't really want to touch this thing very much. You know how you want to touch something, you just hold it away from your body. Where Sydney, she loves her pocketbook. She has it right on her shoulder. She's carrying it, walking around the street. Who's more likely to lose their pocketbook faster, Devin or Sydney?
Devin.
Yeah. The electrons and the atoms work the same way. Now, we just talked about the size of atoms. Where are the larger atoms found, on the left or right side of the periodic table? So
Left.
on the left. So their electrons are found further away from the nucleus, well, that's like your body, okay? Whereas the smaller elements on the very far right-hand side, they're holding their electrons really close. So of those two, which ones are going to be more difficult to take an electron from? The elements on the left or the elements on the right?
On the right.
Yeah, exactly. Okay. So, and that's where the next trend comes into play. So then we talk about the movement, the removal of an electron. Each electron has its own amount of energy, and it's all also dependent on this location in the atom itself and where the atom's found. Okay. So looking at an illustration here, I'm going to kind of bounce around in the slides here. Elements on the left are going to have lower ionization energies than the elements on the right hand side, because it's going to require more energy to remove the electrons on the right as compared to the left. Everyone understand that? That all goes back to size. The bigger the atom, the smaller the ionization energy. The smaller the atom, the larger the ionization energy. Everyone understand that? All right.